everyone. Myself Sravanthi, working as an assistant professor in the Department of Data Science and Cybersecurity in MLR Institute of Technology. Today our topic is intermediate code generation. Here we are going to discuss what is intermediate code, what is the purpose of, what is the need of intermediate code, what are the types of intermediate codes. So let us start. What is intermediate code? So here the intermediate code generation, it is nothing but it is an important phase in the process of compilation. It is the important phase in the process of compilation that converts the high-level source code into machine-independent intermediate representation. Machine-independent intermediate representation. Actually, the intermediate code is the fourth phase of phases of a compiler. See here, we are going to have the 6 phases. The first phase is the lexical analysis. The next one is the syntax analysis. And the third phase is semantic analysis. And the fourth phase is nothing but the intermediate code generator. The fourth phase is nothing but the intermediate code generator. And the fifth phase is code optimization. And the sixth phase is the code generation. So here it is the fourth phase of the compilation. The intermediate code generation is the fourth phase of the compilation that generates a high level, that converts the high level source code into machine independent intermediate representation. Here the fourth phase, nothing but here the lexical analysis is giving me the output as syntax analysis. It generates the parse tree, and this parse tree is given as a input to the semantic analysis. It generates the parse tree, static checker, and it checks the any modifications or any statically it is correct or not. Then it converts or it gives as an input to the intermediate code generator. The intermediate code generator generates the intermediate code. It generates the intermediate code. So that intermediate code is nothing but, here we are going to tell that high level source code is into machine independent code. The intermediate code which is generating, that is nothing but machine independent code. That is machine independent code. This machine independent code is given as an input to the code optimizer. It optimizes the code and it gives as a input to the code generator, and it generates the target code. It generates the target code. So for the lexical analysis, we are going to give the input as a source code. The source code is nothing but the high level language. The source code is nothing but the high level language. It is going to generate the target code. The target code is nothing but we are going to tell it as machine code, machine language, or from high level language to the low level language it is going to generate. So to do this directly, we are going to have the phases of a compiler. These 6 phases it takes place here. So here it is nothing but here we are going to have the 2 pass compilers are there here, single pass and multiple pass compilers are there. So the first 4 phases comes under the front end. The first 4 phases comes under the front end, and the last 2 phases comes under as a back end. The last 2 phases acts as a back end. The first 4 phases are nothing but the front end, and the last 2 phases are the back end. So the front end, it generates machine independent code. It generates machine independent code. Generates machine independent code. Coming to the back end, it generates dependent code. It generates dependent. It is depending and it is machine independent. This is machine dependent. Here, the output which is coming from the intermediate code generator is nothing but the intermediate code, and this is nothing but given as an input to the code optimizer and the code generator to generate the target code. So the first 4 phases are nothing but front end, and the last 2 phases are nothing but the back end, and the back end is nothing but machine dependent, and the first one is machine independent. Same thing. Intermediate code acts as a bridge between the high level source code and the low level source code. Here the output which is generating is nothing but the intermediate code. It is acting as a bridge between the high level as well as the low level. So that is here. It is used in compiler to design the translations process more efficient. Instead of translating directly from high level language to machine code, so what it does is, compiler first it generates an intermediate representation which is independent of both the source language and the target language. This makes it easier to optimize and reuse the compiler backend for multiple languages. See here, I am telling here these are the 4 phases that comes under the front end, and these are nothing but the backend. Here the first 4 phases, but here the parser is nothing but it's a combination of lexical analysis and syntax analysis. And the third one is nothing but the semantic analysis. We can also call it as static checker. This is nothing but semantic analysis. We can also call it as a static checker. And the parse tree which is given as an input to the intermediate code, it generates the intermediate code. It generates the output as a intermediate code. So it is acting as a bridge between the front end and the back end. It is acting as a bridge between the front end and the back end. So the front end is nothing but it is going to generate machine independent. It is machine independent. And coming to here, it is machine dependent. It is machine dependent. See here, this makes it easier to optimize and reuse the compiler backend for multiple languages. See here, the front end is nothing but it is machine independent. So it can be used in any operating systems. It can be compiled any operating systems. C compiler, it is having the Windows. I'm going to run the compilation, C compilation in Windows operating system. To do this, I need to have a front end as well as the back end. I need to do this is nothing but I need to have the front end as well as the back end. So the front end is nothing but here it comes under the 4 phases. The front end is nothing but it comes under 4 phases. These 4 phases nothing but it generates the intermediate code generator, and the last 2 phases comes under the back end. Here these 4 phases is given as an input to the back end and it generates the target code. Suppose the next I'm going to run it in the some other operating system like Linux operating system, for example. Next, again I need to have the front end and again I need to have the back end. But here the front end is nothing but the machine independent. So once I'm generating that can be reused here and I can generate the back end, nothing but the target code. So it is the front end is nothing but machine independent. It can be run on any operating system, but the back end is fixed for each operating system. So here the static checker is nothing but we can also call it as a semantic analysis, which is independent of both source language and target language. So this intermediate representation, which is nothing but it is independent of both source and the target language. So for the parser, we are going to give the input as the source code, and it is given as it generates a parse tree, and it is given as an input to the static checker, and the static checker generates a parse tree and it gives as an input to the intermediate code, and it generates the intermediate code. This makes, so with the help of this, it is making us, it is easier to optimize, and we can also reuse this front end for the different multiple languages. So this is about intermediate code. Intermediate code is nothing but it acts as a bridge between the high level source code and the low level machine code. So what is the need of intermediate code? So it acts as a bridge between high level language and low level language, low level target code. See here, this is the source code, nothing but we can also call it as high level language, which is given as a input, or nothing but the intermediate code is acting as a bridge between the source code as well as the target code. So coming to here, in between this, we are going to have here the 4 phases are going to be there, nothing but the lexical analysis, syntax analysis, semantic analysis, and the intermediate code generator, and then it generates as the intermediate code, and it is given as an input to the target code. So nothing but the intermediate code is acting as a bridge between the source code and the target code. Retargeting is facilitated. Retargeting is facilitated. So nothing but a compiler for different machines can be created. Compiler for different machines can be created by attaching different backends to the existing front ends of each machine. Suppose these are nothing but here a compiler is having the different machines for different backends. These are different backends. We can have a single front end. Nothing but it is as it is a machine independent code. See here, a compiler for different machines can be created by attaching different backends. Different backends we are going to attach for the existing front end, of each machine. Okay, so see here, it is for Windows, I can give, it is for Linux, I can give. So the same front end is given as a input to the different machines. So that is nothing but retargeting is facilitated. Optimization. So by doing this, it optimizes the compilation process. The intermediate code optimizes and it gives as an input to the code optimizer and it generates the target code. So that is why we are going to call optimization is easily available, easily done here. Simplifies the compilation process and ensures better optimization. So the next one is, what are the types of intermediate codes? Actually, there are 2 types of intermediate codes, are the linear form and the tree form. Linear form and tree form are there. Linear form and tree form. So under linear form, the postfix notation and the 3 address code. Under linear form, we can have postfix notation and the 3 address code. Coming to the tree form, we have syntax tree and we also have the DAG. We also have DAG. Here the linear form is nothing but the intermediate code representation is divided into two types, linear form and the tree form. Under linear form, we have postfix notation and 3 address code. Under tree form, we have syntax tree and DAG. Again, this 3 address code is divided into quadruples, triples and indirect triples. So the first one, what is postfix notation? We can also call this postfix notation as reverse polish notation. Nothing but RPN. So it is what type of notation? It is a mathematical notation where operators follow their operands. Operands are nothing but integers. Or constants, any numbers or anything. Coming to the operators are plus, minus, multiplication, into something. See here, operands are followed by their operands. Operators follow their operands. Nothing but here operands following. Operator is followed by operands. Here A, B are operands and minus is the operator. So these are nothing but the operands and this is the operator. Operator is followed by operands. So main use of this postfix notation is we can eliminate the parentheses. And we can also concentrate on operator precedence rules. For example, in my expression, I am having A plus B plus C. Here plus both are having the same priority. So now which one I need to do? Evaluate. So when I am having same priority, I need to evaluate the left associativity. I need to go for left associative. Suppose here I am having multiplication. Here A plus B into C. Now which operator I need to do? Which calculation I need to do? Multiplication is having the highest priority when compared to the addition. So these things will be learned from these operator precedence rules by simplifying the representation of expression. It is mainly used in the stack based method. It is mainly used for evaluating the expressions in stack. In using stack, we will evaluate these postfix expressions. Example, x equal to y plus z into a. Here I am having y plus z, brackets are there, nothing but the parentheses are there. X equal to y plus z into a. Here the first I am going to eliminate these parentheses, nothing but y operator should be followed by their operands, y z plus into a. So it can be written as yz plus a into. Why? Because here this is one expression, one operator, and this is one operator. Operand. This is one operand and this is one operand. There is a operator is lying here. So that is nothing but, as it is a postfix expression, left, right and root. Will be written here. So the next one, A plus B into C plus D. So here what we are having here, parentheses are there. So first eliminate the parentheses and write it in a postfix expression. Nothing but the operator is nothing but, it should be like followed by the operands. So I can write A plus B as AB plus C plus D. I can write it as CD plus. In between there is a multiplication operator is there. This is one operand, this is one operand. So how can I write here? AB plus CD plus multiplication. Same thing is written over here. So first we need to eliminate the parentheses, then follow the precedence rules and simplify the given expression in the form of postfix expression or postfix notation. We can also call these postfix expression as reverse polish notation. So the next one is syntax tree. We can also call this syntax tree as abstract syntax tree. We can also tell it as in a shortcut AST. It is in the form of, the name itself tells, tree is nothing but, it is a tree structure. It is a tree structure and it is in the form of hierarchical representation. We are going to represent it in a hierarchical form, nothing but tree form. Here each leaf node, the leaf node represents operands. See here the leaf nodes are representing the operands and the internal nodes are representing the operators. While each internal node represents operator and leaf node represents operands. The syntax tree is nothing but simplified version of the parse tree. We are going to simplify the parse tree which is generated and we are going to write it in a syntax tree. It provides hierarchical representation. It is a tree structure. Tree is nothing but it is a hierarchical representation of the source code where nodes denote the operators and operands. Here each node is there. These are all the nodes. Circles are nothing but nodes. Internal nodes are operators and the leaf nodes are the operands. All these nodes are nothing but it denotes operators and operands. These are operators and these are operands. These are operands. And the connection between them is nothing but we are going to call it as edge. So this shows the relationship between them. This shows the edge shows the relationship between these two operands or between the two nodes. It shows the relationship between the two nodes. The syntax tree is nothing but we can call it as a abstract syntax tree. It is in the form of a tree format. We can also tell the tree is nothing but it is a hierarchical structure where the internal nodes will be having the operators and the leaf nodes are nothing but the operands. Leaf nodes are nothing but the operands. The edge shows the relationship between the two nodes. See here, draw a syntax tree for the string a plus b into c minus d. A plus b into c minus d. So, which is the highest priority I am having here? The multiplication is the highest. So, let me write here operator and leaf node is b and c. The next plus and minus. So, let me evaluate plus a plus b into c. A plus b into c. Left root right. Left root right. So, nothing but a is left plus b into c. It's completed. The next one I am having is minus d. Minus d. It is in the form of what? Infix operation. So, infix nothing but, so left root right. So, nothing but the root nodes, the leaf nodes are nothing but the operands and the root nodes are nothing but internal nodes are the operators. So, left a plus b into c minus d. Right? So, this is nothing but, so first it starts from here, left. So, there is a left operator. There is a left operator that is nothing but the leaf node. So, a is written here. A is written here plus right. It comes over here. This is a root node again. And it comes here b. Next root. Next c. It goes back. Root right. So, this is nothing but a plus b into c minus d. A plus b into c minus d. So, this is about syntax tree. So, the next one is in the tree form is the DAG. So, DAG is similar to the syntax tree, but here we are going to eliminate the common sub-expressions and we are going to reduce the redundant computations. We are going to construct a syntax tree. From these syntax tree, we are going to eliminate common elements. We are going to eliminate, that is nothing but we are going to call it as a DAG. We are going to eliminate the common sub-expressions and we are going to reduce the redundant computations in basic blocks. So, that is nothing but the DAG. The DAG is nothing but directed acyclic graph. It is similar to syntax tree. We are going to generate the syntax tree. Then we are going to apply the DAG form. Nothing but we are going to eliminate what are the common elements are there. If the same is repeated, we are going to give a connection and we are going to eliminate. So, by using this, we are going to optimize the code. By doing this, we are going to optimize the code. See here, A is equal to, this is nothing but the assignment operator. A equal to B into, this is minus C is nothing but unary minus. It is unary operator. Plus B into minus C. Plus B into minus C. So, for this, I have constructed here the abstract syntax tree or nothing but I can call it as syntax tree. Here, the first one I am having is B into C minus C is there. So, it is minus C is nothing but it is a unary minus. It is nothing but unary minus. So, directly I am going to write it as U minus. I am going to write it as U minus. So, the first we are going to construct B into minus C. B into minus C. So, for that, this is the first I am having unary operator. So, minus C, B into minus C. The next one is plus B into minus C. A equal to assignment operator. A equal to assignment operator. So, this is nothing but the abstract syntax tree. Now for these abstract syntax tree, we are going to construct the DAG. See here, I am having here both B into minus C, B into minus C. The same thing is repeated twice. The same thing is repeated twice. Instead of writing 2 times, I can write it 1 time by using this DAG concept. So what I am doing here is A equal to plus operation plus here multiplication, here I am having, here I am having. So both are pointing to the same thing, B minus C, B minus C. So instead of writing 2 times, I am going to write it 1 time and I am going to give as operator as cyclic operator here plus into. So nothing but what it does is, first it reads B into minus C plus B into minus C. These operation done by this thing. Okay, instead of writing 2 times, I am writing only 1 time and I am giving this as repeat it twice. So and it is going to be done and the result is stored here. By doing this, we are going to optimize the code. Instead of writing 2 times, we are going to reduce the graph or reducing the tree. So that is nothing but directed acyclic graph. So the next one is 3 address code. So the 3 address code is nothing but it is an intermediate representation used in compilers to simplify the translation of high-level programming language into machine code. Here we are going to generate the intermediate code. So these intermediate code is consisting of the 3 address code. Here by using these 3 address code, we are going to simplify the translations. We are going to simplify the code. The 3 address code, we are going to simplify the code. Here each instruction typically involves only at least or at most 3 addresses. Nothing but at most 3 operands should be there. More than that operands are existing. We are going to simplify that expression. So here the 3 address code is nothing but here each instruction should have at most 3 addresses or nothing but 3 operands. We are going to write 3 operands or nothing but we are going to store or we are going to allot 3 addresses for it. 3 memories we are going to allot it. See here one example, x equal to y plus c. See here in the RHS part, we are having only the 2 operands, 1 operator and 2 operands are there. 2 operands, y and z are the operands and plus is nothing but the operator. And here x equal to. So total how many operands I am having? 3 operands are there. 3 operands, x, y and z are the 3 operands I am having and I am having only 1 operator, that is nothing but some addition operator. In the RHS side, we should have only 1 operator should be there. So if I am having more than 1 operator in the RHS side, we need to simplify, and if we have in the RHS side more than 2 operands, we need to simplify it. So that is nothing but the 3 address code. See here the next example, A equal to B plus C into D. Here totally I am having 4 operands are there. A, B, C and D. These are the 4 operands are there. And how many operators I am having? 2 operators are there in the RHS side. But according to 3 address code, we should have, it should involve or it should have at most 3 operands should be there. But here I am having 4 operands are existing here. So now we need to simplify this code. So how we are going to simplify this code is by using some temporary variables. We are going to simplify this. Expression. So how we are going to do here? So B plus C into D. Which is having the highest priority? C into D is having the highest priority. So in each 3 address code, we should have at most 3 addresses. So T1 is nothing but I am giving one temporary variable. We can give T1 or T2 or anything. We can give as a temporary variable. So what I am going to have? C into D. Here total how many operands are there? 1, 2, 3. 3 operands, and in the RHS I have only 1 operator. So the next one is T2 is equal to. So what I am having here? B plus C into D. Where it is stored? C into D. It is stored in T1 operator. It is stored in T1. So T1 temporary variable. So directly I am writing T into T1. Instead of writing C into D, I am going to write T1. Why? Because we are going to reduce the expression. We are simplifying the expression. Now B plus C into D. So that is stored in T2 variable. Now, what I'm having here, A equal to, so where this whole thing is stored, it is stored in T2. Now, I have simplified this expression into 3 steps. I have simplified these expression into 3 steps. So, here in the RHS side, we should have only one operator should be there, and totally we should have in 3 address code, 3 operands should be there. If I am having more than 3 operands, we are going to reduce the expression. We are going to simplify the expression by using some temporary variables. So, the 3 address code is again divided into 3 types: quadruples, triples and indirect triples. The quadruples, the name itself tells quadruples is nothing but it is consisting of 4 fields. It is consisting of 4 fields. First one, operator, argument 1, argument 2 and result. So, we are going to have operator, argument 1, argument 2 and result. Argument 2 and result. So, these are the things that are available in quadruples. See here, I have taken one example. Plus is nothing but operator. This is argument 1, argument 2 and this is result. This will be in the form of operator, argument 1, argument 2, result. All this. So, how can I write it in a form of a expression? Nothing but x equal to y plus z. Argument 1 plus argument 2. So, I can write this one as T1 equal to C into D. This I can write it as T2 equal to B plus T1. B plus T1. Next, I can write here A equal to T2. A equal to T2. Here minus is nothing but argument 2, no operation is there. So, just I am showing it with blank line. So, A equal to T2. So, quadruple is nothing but it consists of 4 fields. The 4 fields are, first one should be operator, second argument 1, third one argument 2 and the last one should be result. So, these can be written as this one. If I simplify it, we can write it in the form of an expression form. So, the next one is triples. So, the triples is nothing but the name triple is nothing but it consisting of 3 fields. Here we are going to eliminate result field. We are going to eliminate result field. Then where we are going to store the result? We are going to store it in the positions. We are going to store it in the positions. Previously we have used for quadruples, we have used the temporary variables. Here we are going to use the indices. We are going to use the indices by using some numbers, some addresses. I mean to say is, we are going to store it in the form of a positions at 0 position, at 1 and 2 positions. So, it uses positions, nothing but we can call it as a indices. Instead of temporary variables, we are going to use the indices. See here, B minus C. How can I write this one? Minus operator minus B, C. B, C. Operator, argument 1, argument 2. So, this is also minus B comma C. And this is nothing but plus operator. Where this is stored? At 0 index. 0 index. And this is stored at 1 index. Nothing but the whole thing is stored in second index. The whole thing is stored in second index. I can assign it to A. We can assign it to A. So, the next one is indirect triples. Indirect triples. Here we are extending the triples by storing them in arrays with pointers. Nothing but here we are going to have one extra table will be there, that is nothing but pointer table. It stores the addresses of these indices. We are going to store these in addresses of these indices in pointer variable. A separate pointer table is used. It makes code reordering easier. So, by using this pointer table, we can easily reorder it. The code can be reordered. See here, example A equal to B minus C plus B minus C. I have written by using some temporary, nothing but indices I have used 0, 1 and 2. Okay. So, but just mentioning here with T0, T1, T2. Anything we can take. Indices we are maintaining. Minus B comma C plus T0, T1. T0, T1. Now, this T0 is stored at address location, some P0. This T0 is stored at address location, that is nothing but P0. And this T1 address is stored at P1. And this T2 address is stored at P2. This T2 address is stored at P2. So, these things we have done in the triples. Coming to here in indirect triples, we can have the instead of T0, I will be placing here P0. Why? Because the T0 is stored at the pointer at the address location P0. and T1 is stored at the address location P1. So that is nothing but indirect triples. Coming to the triples, we are storing it in the indices. Coming to indirect triples, we are going to store it with the pointers. Nothing but we are going to use the pointer table. That indices are going to be stored in some pointer variable. Nothing but some address location. These pointer variables, these indices are stored, and these pointer tables are used here. Pointer variables are used over here. So this is about 3 address code. So today we have discussed what is intermediate code. Intermediate code is nothing but it is the bridge between the high level language and the low level language. It generates the intermediate code. It is the fourth phase of a compilation. Here it generates the semantic analysis as the output is given to the intermediate code generator, and it generates the intermediate code that is nothing but the machine independent code, which acts as a bridge between the high level language and the low level language. Then we have discussed about the types of intermediate codes. There are 2 types of intermediate codes, linear form and tree form. Under linear form, we have postfix notation and 3 address code. Again, the 3 address code is divided into triples, quadruples and indirect triples. And the next one is we are having syntax tree. Syntax tree is nothing but it is an abstract syntax tree where we are going to generate the parse tree, and that we are going to optimize, or we are going to eliminate the redundant expressions that we have called it as DAG, nothing but directed acyclic graph. Thank you.